So, in this lecture, I am going to talk about electromagnetic theory of dispersion. First of all, I will talk about brief history and the definition of dispersion, and then I will derive the dispersion relations. So, first of all, let us talk about dispersion and its brief history. So, consider a prism. So, if light is made to incident on it, white light, then this gets deviated from its path, and it will deviate in this manner, and it will split into different colors. So let me do one thing. Let me choose different colors. So this one is the red, and this one is blue or the violet. So it will split, and in between we will get different colors. So in this manner, here it will go like this, and here it will go like this. So this is the red part, and this is basically, and this is corresponds to violet region. So that means what is happening when white light is made to incident on a prism or some transparent medium, it's split into its constituent colors, and this phenomena is known as dispersion. Or what is happening, if I talk about in terms of words, then that means what dispersion is doing means we can say that different colors refract at different angles, and we call this as dispersion. Or in other words, what I can say, that dispersion is the phenomena of variation of index of refraction of a medium with the wavelength of the incident electromagnetic radiation. in general, index of refraction, index of refraction n has been found to decrease with the increase in lambda or wavelength, with the increase in wavelength. So for all these things, in 1836 Cauchy derived empirical formula for the dependence of refractive index on wavelength of the medium in the region of normal dispersion. I will talk about normal dispersion later on. So this was the formula which was tested empirically by Cauchy, and these AVC are the constants. Then in 1871, Salmier deduced a dispersion formula of general applicability on the basis of elastic solid theory of light. Then around 1900, Lawrence, H.A. Lawrence, developed the electromagnetic theory of dispersion by assuming that atomic dipoles in the material medium execute forced vibrations under the influence of electric vector of incident electromagnetic radiation. These atomic dipoles are created in the medium medium due to the relative displacement of electrons of electrons and positive ions under the influence of electric vector, under the influence of electric vector. And he also assumed that electrons are bound to the nucleus by harmonic forces, and these harmonic forces causes a force minus gamma x acting on the electrons. So this is one force term, and if E is the electric field, then this causes force EE acting on the electron. And there is another, this is one term, this is another term, and this is third term. That is, there is damping frictional force will also be acting on the system. So therefore, damping frictional force will be represented as minus alpha dx by dt acting on the system. So therefore, keeping these three forces in mind which are acting on the system, equation of motion can be written as, so equation of motion becomes md square x over dt square plus alpha dx by dt plus gamma x must be equal to EE. So therefore, this equation will simplify to d square x over dt square plus alpha by m dx by dt plus gamma by m x plus e by m equal to. So let us consider the case when damping is small and in that case we will define resonant frequency as omega naught square, or simply omega naught is equal to gamma over m under the root, or in other words, I can say that omega naught square is equal to gamma by m. Also choose that G naught is equal to alpha by m. So if I use these two, then this above equation reduces to this d square x over the vector quantity d square x over dt square plus g naught dx over dt plus omega naught square x is equal to e by m into e. In operator form, this equation can be written as d square plus g naught d plus omega naught square x is equal to E by ME. Now let us incorporate polarization into this equation, and let me number the equations, and let me call this as equation number 1. This is equation number 2. This is equation number 3, and this is equation number 4. Now to incorporate polarization, what I will do, let us define polarization. Polarization of a dielectric is dipole moment per unit volume and displacement of a charge E to a distance x produces dipole moment Ex. So if there are n dispersion electrons in the system, electrons per unit volume, then total polarization will become, so this P is equal to n small p. It is the dipole moment per atom. So it can be written as NEX. So keeping this in mind, let us multiply equation number 4 by NE on both sides. If we multiply that equation with NE on both sides, equation number 4, then equation will become d square plus g naught t plus omega naught square x NE is equal to NE E by ME. So this equation simplifies to d square plus g naught t plus omega naught square, and this will become polarization vector, total polarization of the system, and it is Ne square by Me. And let me call it as equation number 5. Therefore, this equation will become d square p over dt square plus g naught dp over dt plus omega naught square into p. It must be equal to Ne square over Me. This is equation number 6. And since E is a plane wave, so that means it can be written in the form of exponential. So therefore, I can write down this equation as d square p over dt square g naught dp over dt plus omega naught square p. It must be equal to Ne square by m E naught exponential minus iota omega t. Let me call it as equation number 7. Now again, from equation number 5, we can write this polarization vector is equal to Ne square by m E vector 1 over t square plus g naught t plus omega naught square. So now for steady state solution, Let us assume that d is equal to minus omega, which implies d square is equal to omega square, as we talk about it in the earlier, and it's a simple mathematics. So using this equation number 8 become this P is equal to n e square by m e vector divided by minus omega square minus g naught iota omega, sorry, plus is there, plus omega naught square, and this P over E, if I bring this E towards this side, then it is n e square by m 1 over omega naught square minus omega square minus iota g naught omega. Let me call it as equation number 9. Now let us define dielectric constant. Of the medium as that epsilon is equal to 1 over 4 pi. Also we know that dielectric constant is a imaginary number. Sorry, it's a complex number. For this you can follow the book Optical Theory of Solids by Bhutan. It's a very beautifully written book. So from here I can define the refractive index as this n is equal to c by v, or this is epsilon mu under the root, and this is nearly equal to this dielectric constant under the root, because the value of mu is nearly equal to 1 for dielectric medium. At optical frequencies. So if I use this value as 1, then it will be equal to this one. So therefore, what I am concluding, that also we know that n is a complex number. So that means, sorry, if epsilon is a complex number, which makes refractive index also complex number. So for that I will expressing it as n star square is equal to this, using this equation. I will use this equation number 11, and if I use the value of epsilon from equation number 10, so it is equal to 1 plus 4 pi p by e. So that means n star square minus 1 is equal to 4 pi p upon e. So therefore, expression for refractive index, it will become 4 pi n e square over m. It is 1 over omega naught square minus omega square minus iota g naught omega. So this is the equation for the refractive index. So here, up to this, what I considered, that medium contains oscillators, and each oscillator having same force constant. constants and same natural frequency. But if there are n molecules per unit volume, if there are n molecules per unit volume such that kth molecule has Fk oscillator with omega k and gk constants and so on. So if I consider this consideration, then this total polarization can be written as summation over k, and this can be written as Ne Fk xk. So if I use this, then equation number 6 will become, if I use this consideration, then equation 6 becomes d square pk over dt square plus gk d square pk over dt plus omega k square pk must be equal to Ne square Fke and it's divided by m, and this leads to Pk is equal to Ne square over m Fk E over omega k square minus omega square minus iota gk omega, and let me call it as equation number 30. And this leads to the refractive index as we have calculated from here. In the similar fashion, we will get the same expression for the refractive index, but it is little bit different with the summation sitting with it. So therefore, refractive index will become 4 pi Ne square over m summation over k Fk divided by omega k square minus omega square iota gk omega, right? So this is the expression for refractive index, and this equation is known as dispersion relation. So with this lecture is finished, and in the next lecture I will talk about this dispersion relation in detail and how it is used to calculate the Cauchy's and Saint-Maire's dispersion formula. So thanks for watching it.